এক্সিলেন্সে সকলকে স্বাগত। আমরা যারা বিজ্ঞান অনুরাগী, পদার্থবিজ্ঞান অনুরাগী ছাত্রছাত্রীরা এই ওয়েবিনারে অংশগ্রহণ করছি, স্যার আছেন, স্যারের টক শুনছি, তো আমাদের মনে প্রশ্ন জাগতেই পারে যে এই অনলাইন ফান্ড রেজিং ওয়েবিনারটির উদ্দেশ্য কি, অর্থাৎ ওয়াই ফান্ড রেজিং। তো এর পিছনে যে উদ্দেশ্য সেটি হলো দুটো, একটা হলো রিবিল্ড বেঙ্গল এবং একটি হলো সায়েন্স উইথ সোসাইটি। অর্থাৎ বিজ্ঞানকে কিভাবে আমরা বিজ্ঞানের স্টুডেন্ট, এবং বিজ্ঞানের স্টুডেন্ট হিসেবে আমাদের সমাজের প্রতি কি দায়িত্ব আছে এবং আমাদের সমাজের প্রতি কি কি করার আছে। এবং রিবিল্ড বেঙ্গল, আমরা যদি বেঙ্গল শব্দটাকে দেখি, বেঙ্গল কোনো নির্দিষ্ট রাজনৈতিক বা ভৌগোলিক সীমাবদ্ধ কোনো ভূখণ্ড নয়। বেঙ্গল একটা ধারণা। কিসের ধারণা? বেঙ্গল হলো একটা ইউনিটি এবং একটা সলিডারিটির ধারণা। অর্থাৎ আমরা যদি দেখি ইতিহাসে চলে যাই, তাহলে আমরা দেখবো 1857 খ্রিস্টাব্দে মহাবিদ্রোহ বা 1905 সালে বঙ্গভঙ্গ আন্দোলন, পরবর্তীকালে মন্বন্তর, প্রতিটি ক্ষেত্রেই যে কমন থ্রেড সেটি হলো বাংলা এবং বাঙালির একত্রিত হয়ে থাকা এবং একত্রিত হয়ে ক্রাইসিসের মোকাবিলা করা এবং সলিডারিটি জানানো, অর্থাৎ একে অপরের পাশে সহমর্মিতা জানানো। তো আমরা দেখছি যে 2020 সালে কোভিড কিভাবে একটা গোটা সমাজকে অর্থনৈতিক ক্ষেত্রের দিক দিয়ে হোক, সামাজিক ক্ষেত্র দিক দিয়ে হোক, সমস্তভাবে বিপর্যস্ত করে তুলেছে। এবং তারপরে আসে আমফান এবং 2021 সালে কোভিডের সেকেন্ড ওয়েভ এবং ইয়াস ঘূর্ণিঝড়। এই সমস্ত কিছু প্রভাবে বাংলার উপকূলীয় অঞ্চল তো বটেই, সমগ্র বাংলাই ক্ষতিগ্রস্ত এবং বিপর্যস্ত। তো সেই ক্ষেত্রে আমরা সেই ক্ষতিগ্রস্ত বাংলার পাশে কিভাবে ফিজিক্স ফোরাম, ফিজিক্সের স্টুডেন্ট হিসেবে আমরা কিভাবে পাশে থাকতে পারি, তো সেই ভাবনা থেকে আমাদের এই ওয়েবিনার সিরিজের কথা ভাবা। তো একটি পেমেন্ট লিঙ্ক, একটি কন্ট্রিবিউশন লিঙ্ক আপনারা দেখতে পাচ্ছেন। তো আপনারা সেই কন্ট্রিবিউশন লিঙ্কে গিয়ে যারা অডিয়েন্স আছেন বা যারা শুনছেন বা শুনছো, তো সকলেই গিয়ে সেটিতে ডোনেশন করতে পারেন নিজের সামর্থ্য মতো, নিজের ইচ্ছে মতো, নিজের ক্ষমতা মতো। সেই সামান্যতম ডোনেশন দিয়ে আমরা যে ডোনেশনটি আমরা নেব, যে ডোনেশনটি আমরা পাবো, সেই ডোনেশনটা আমরা দিয়ে দেব যা
We are live again from the Facebook page and the YouTube channel of Physics Forum Kolkata. Thank you for joining today. We all have just heard in the previous video that we are organizing this webinar as a part of a solidarity. It's not a celebration and all. I feel it's our duty, not only our responsibility to stand by our own people in need, it's our duty actually. The contribution link, as Shomujit said, is below. So feel free to contribute if possible and contribute as much as you can if possible. And this platform, Physics Forum, it felt the need to come forward and work tirelessly as much as possible. So all the money we will collect here will be given to the frontline workers or organizations who are working tirelessly in this situation. Now I want to call a member of Physics Forum, Arijit Ta, to tell something about this cause. Arijit. Arijit?
Hello,
Okay.
good afternoon, everyone. So, hello, Ravanash. How are you? Hope you are well. So, we know about the cause that during from since the 2020 India and our beloved Bengal is facing two unexampled lockdown, and there are two ferocious cyclones hit in our coastal areas. So there is a devastation about millions of people are lost their home, and there's a lot of problem in our beloved Bengal. So in this way, in this situation, Physics Forum Kolkata is trying to provide a solidarity, and we know that science is nothing different from society. So we are trying to do something like science for society and science with solidarity, so that the students who belongs from science and mainstreams of from in Bengal University, so they can uh, be there as a part of solidarity and be a part of this work. So rebuild Bengal is some kind of things যেটা আমরা করার চেষ্টা করেছি। তো হ্যাঁ, মানে কঠিন সময় যাচ্ছে, কঠিন সময় হয়তো অনেকে মনে করছেন যে ইটস কার্নিভাল অর সামথিং, বাট অ্যাকচুয়ালি এটা কোনো কার্নিভাল বা উদযাপন নয়। দিস ইজ নট এনি কাইন্ড অফ সেলিব্রেশন, রাদার ইট ইজ এ দিস গ্যাদারিং অফ মাইন্ডস ইজ সামথিং লাইক এ what do we say, it's like a solidarity to show that we are also in this part, and we are also very conscious in this grim situation. So that's why the coherence আমরা চেষ্টা করেছি করার। আর যে ব্যাপারটা আরো বলার, যে কোহারেন্স বা এই টার্মটা অনেকে ফিজিক্সের স্টুডেন্টরা খুব ভালোভাবে উপলব্ধি করেছে বিভিন্ন জায়গায়, যে কোহারেন্স ইজ এ কনসেপ্ট অফ ফিজিক্স। আমরা চেষ্টা করেছি অন্তত ইন দিস সেমিনার এই কোহারেন্স শুধুমাত্র ফিজিক্সের কোনো একটা পার্ট বা টার্ম নয়, নট এ টার্মিনোলজি অনলি ফর ফিজিক্স স্টুডেন্টস, রাদার উই আর ট্রাইং টু প্রোভাইড a theme, a motto, the cohesion of society and the cohesion of excellence. So that's all about this seminar. So hope আজকে second we are having Professor Supratik Pal from ISI Kolkata. We are very grateful to him, and আমরা খুবই উৎসাহিত উনি আমাদের থাকছেন এই সেমিনারে। So let's see what happens. Thank you, everyone.
So thank you, Arijit, for coming and telling us about the cause. So now we will start the webinar. First of all, let me tell you that you can ask questions in the comment section of Facebook and YouTube as well. We will pick the questions and ask our respected lecturer to answer those questions and at the end of his lecture. So feel free to ask. Now, without any further ado, let's call our respected guest lecturer, Dr. Supratik Pal. He is a faculty member of ISI Kolkata, and today's topic of lecture is unveiling the mysteries of our universe with telescope. So, thank you, sir. Thank you for coming. One second. Okay.
So, shall I share my slides now? Or
So, pardon me for interrupting. So, we'll be very grateful, sir, if you tell the audience about the cause we are here today, Rebuild Bengal, and ask them to be here.
Okay, sure. I'll start with that thing.
Sure, sir. Okay.
Yeah.
It's up to you, sir.
So, is this the right time to share my screen? Or
Yeah, sure.
That's it. Yeah, sure. Can you see my screen right now?
One second. Yes, sir. Yes, sir.
Okay. So let me put my video off just to set the bandwidth and let me, yeah. Okay. So you see my slides, right?
Yeah, yes, sir.
Okay, that's it. And before I start, let me ask, how much time do I have?
Sir, you can on your video also there is a system, so you can share both your screen and your video also.
Okay.
So it will be helpful for the student to interact and okay, sir,
Okay.
thank you.
So can you see me right now?
Yeah, yes, yes, sir. Yes, sir.
That's good. That's good. And you can see my slides as well, right?
Yeah.
Okay, sure. How much time do I have all total?
So you can take time, sir.
Okay.
1.5, 2 hours. Okay, no
Yeah,
problem, sir.
thank you very much. So let me start right now.
Yeah, yes, yes.
Okay. That's good.
Up to you, sir. Thank you, sir.
Okay. So let me first thank the organizers for inviting me to this beautiful program. As you have already heard about, this program has twofold purposes. Number one is to promote science, in particular physics, to the common mass as well as to the younger generation, so to say, those who are doing their UG and PG level studies in physics. But at the same time, I'm pretty impressed that these guys are doing their philanthropic job on top of this science understanding of science and all these things. I'm quite aware of their developments and etc for the last 1 year or so. So they're promoting science as well as they're promoting the social causes and all these things towards this cyclone and also this pandemic situation and all these things. So hats off to them for this wonderful initiative, and I do hope that they will continue doing these things in future as well. And as they have already told, let's just share our part, contribute our part, and come up voluntarily to this wonderful cause and contribute to whatever extent is possible for us. I myself place that I have already contributed to some extent earlier, but I'll once again contribute to this wonderful cause, and I request all of you that please come up voluntarily and contribute so that this purpose can be completely successful, both in the context of science as well as in the context of philanthropy, so to say. Okay, so having said this, let me now begin my talk by thanking the organizers once again for giving me this platform to interact with you guys during this pandemic situation, because I always love to interact with the young minds face to face, but due to this pandemic situation for the last more than 1 year or so, this is not being able I'm not being able to do that. But this webinars business and etc, they are doing wonderful jobs, and through this platform we have been able to interact with the younger generations as well, and at the same time we are being able to promote science and keep on doing science, because whatever the situation may be, as science students we must keep on doing science, and that will basically keep us alive. So this is a wonderful platform of doing that. Okay, so today what I'll do is, for the next 1 hour or so, I'll basically try to tell you a story of the mysteries of our universe that we have been able to decode using different telescopes. So basically, I have been fascinated about this story for the last several years or so, and I'll try to share my experience as well as share the story with you guys. So don't just consider that I'm someone here as a teacher and I'm telling you some kind of expert level topics and all these things. I'm just one among you guys, and just so that is what the purpose of this talk will be. So we'll just follow a storytelling mode without going into technical details. So I'll just show you some slides and stuff where you will see some pictures and diagrams and etc. And using that, I will basically discuss about the story of our universe that we have been able to understand, we have been able to learn using telescopes for the last 100 years or so. So this will be the purpose. And I will do this thing more or less chronologically or with a historical perspective for the last 100 years or so. So this will be the major target of my talk. And as the organizers have already told you, If you have questions, I usually face so many questions during my talk. So if you have questions, you can write that down, and I'll be happy to take off some of them at the end of my talk. Okay. So this is the beginning. I'm pretty sure all of us know about this guy. He is Albert Einstein, famous scientist Albert Einstein, who actually was one of the pioneers of modern cosmology and astrophysics, so to say. And I'm quite sure all of you have heard about his general theory of relativity, on which our modern cosmology and astrophysics is based on. But this is not directly related to general theory of relativity, or this is somewhat indirectly related to GR. This is a cover page of the Science magazine that was published in 1998, and that deals with a particular kind of surprises that people have observed using telescopes that year, and that information is called the accelerating universe. I'll come to this point later on, but I'll try to bring your attention to the line that is following the word the accelerating universe. Here this is written breakthrough of the year. So as it turned out that the accelerating universe, the invention of the accelerating universe, that was the breakthrough of the year 1998. So what I will do is that starting from say early 1990s onwards, I will basically try to bring forward some of the breakthrough inventions of cosmology and astrophysics using different telescopes. That will be my target. So as I said, I will basically develop everything chronologically without going into technical details. I'll just follow a storytelling mode, and I'll try to do this thing slowly and slowly. So let's begin with this. All of us know about this thing. This is the night sky, and in order to know this, we don't need to know about science at all. Even as a layman, if we look on the outer sky at night, and if the sky is really clear, then using our naked eye, we can see that outside our Earth, Mother Earth, and all these things, we have lots of stars and planets and etc. They are there in the night sky, and this we have been able to know about this thing. At least we have been able to see about this thing for years and years. Okay, but the major point is that this night sky is haunting the civilization for long, because people are always, I mean, right from the cave ages and all these things, people are always trying to understand what we can see using our naked eye. Is that knowledge sufficient or not? If this is not sufficient, then let us try to go beyond our naked sky, because all of us know our eye, that is a lens, that has got some limitations. So if we can improve against the limitation of our naked eye, and if we can develop some kind of instrument, then maybe we would be able to understand about the outer universe, or maybe the night sky, in a much better way than what we can see using our naked eye. And this is the target, to develop something which is called telescope, and that is the major point of discussion today. As all of us know, this is basically a cartoon. This is the first telescope. This is the cartoon, as I said. This is the first telescope that was invented by Galileo Galilei around 400 years back. And during the last 400 years, we have come a long way. Science has developed, technology has developed, our understanding of the universe has developed. And I am basically going to explore some of those developments in the next 1 hour or so. So using those telescopes, this is actually the first breakthrough using those telescopes. As all of us know, this is something we have learned about from our good old school days, that Copernicus, he first proposed that in our solar system, Sun is actually in the center, and Earth, along with some of the other planets, these 9 planets, they are basically rotating around the Sun. This is something was proposed by Nicolaus Copernicus, and after the discovery of this telescope, Galileo Galilei for the first time proved that yes, indeed, what Nicolaus Copernicus was saying, this is correct, that yes, indeed, in our solar system, Sun is in the center, and our good old Mother Earth, along with other planets, they are rotating around the Sun. So this is the first breakthrough with telescopes, but I'm not going to discuss about this thing in details, because as I said, this was discovered 400 years back, and we have come a long way. Right now, equipped with our advanced knowledge of science and technology, as well as other developments in other sphere of our life, we have been able to build different telescopes. In fact, we have been able to build hundreds of telescopes with highly sophisticated kind of technology and science and all these things. I'm going to discuss about some of them in the next 1 hour show. So broadly, right now, all these telescopes, they can be broadly categorized into, based on two different classes. Number one is that based on wavelengths. As we know, using our telescope, what we do, we basically catch some waves that are coming from the outer universe. Okay, so coming from outer space. So we basically catch some waves, and as all of us know from our school days, that waves have two fundamental properties. One is the wavelength, the other one is the frequency. So using this wavelength, what kind of wave we're going to catch, depending on that, it has got a particular kind of wavelength. And we know the product of this wavelength and frequency gives the typical speed of propagation of signal. Here, if you call it light, then the speed of propagation of light. So using typical kind of wavelength, we are basically trying to catch. We can categorize different telescopes into different parts. Like it can be of optical range. Optical telescope is something we have. I'm pretty sure all of us have seen this optical telescope, because this has got a typical wavelength, as all of us know, of the order of 10⁻⁴ centimeter. That is typical, the Vibgyor kind of thing we talk about. But there can be several waves that are coming from different astronomical objects or from the universe as a whole that can have wavelengths much below the optical, like soft X-ray, hard X-ray, etc., etc., or above the optical. The wavelengths can be larger than the optical range. They can be infrared, radio wave, and a part of that can be microwave kind of thing. So those are the things which we cannot directly see using our naked eye or using optical telescope, because their wavelengths are much beyond that. In order to catch them, we need to build different telescopes which are not optical kind of thing. I'll discuss about some of them in details, and that will play a very important role in our today's discussion. So based on what kind of wave we are going to catch, the telescopes can be broadly categorized into these classes. And of course, based on location, where actually they are located, they can be broadly categorized into three classes. One is ground-based. They can be located somewhere on the Mother Earth. At some places, they can be placed underground. I'll give one particular example of that as well. And they can be space-based as well. By space-based telescopes, all of us know that is called artificial satellite. So based on locations, we can broadly categorize those telescopes into three classes. And armed with all these kinds of telescopes with highly sophisticated technology, etc., etc., and we have got plethora of data using these telescopes. By analyzing that data, we are basically trying to understand the universe as a whole, or different phenomena of the universe, which we call astrophysics or cosmology as a whole. So I'll just, as I said, I will basically give you some examples of these telescopes. After that, I will come to the major breakthrough of our understanding of the universe using telescopes, slowly and slowly. So these are two typical ground-based telescopes. As I said, these are just representative examples. We have hundreds of different examples as well. And I will come to some more examples in course of my lecture. But right now, what I'm trying to focus on are two ground-based telescopes. One is called the Vera Rubin Observatory. This is something that is in the design stage. This is somewhere in Chile, and that will come to limelight roughly in 2023, not far away. This is called Vera Rubin Observatory, and that is going to be a very interesting observatory so far as our knowledge of our universe is concerned. I am showing you this particular example because of the name Vera Rubin Observatory. I will tell you why due course. And the second one is called 30-meter telescope. This is still in the planning stage. This telescope will be developed somewhere in Hawaii, and this is going to see the limelight by 2027 or so. The interesting point over here is that why this has been given this name, 30-meter telescope. Just try to think over it a little bit and try to get surprised that the mirror, the principal mirror that this telescope, that will not be a single mirror, that will be a combination of mirrors, and the effective diameter of that mirror will be of 30-meter length. Just try to pause a minute and think over it. A 30-meter lens, this is the diameter. So this will be the size of a big football ground, so to say. We have been we are being able to know about different telescopes, etc., etc. We come across those telescopes, and here I am going to talk about some telescope. I'm not going to talk about in details about this telescope, but I'm just giving you one example that within a few years we'll be able to build a telescope. The effective diameter of the lens will be of size of a big football ground. So it's a huge one kind of thing, and we'll be able to understand our universe to a great extent using this highly equipped, highly advanced and highly sophisticated telescopes. So these are two examples of ground-based telescopes, but as I said, I'll come to other ground-based telescopes depending on what kind of physical problem I'm going to discuss in details later on. One particular example of space-based telescopes is Hubble Space Telescope. I'm pretty sure that all of you have heard about this telescope. I'll discuss about this telescope in a bit details later on, based on the particular physical problem I'm going to discuss. This Hubble Space Telescope was proposed long back by Edwin Hubble in 1940s. This started running in 1993. And this is giving us enormous amount of data for the last 27 years or so. I will focus on some kind of data that will be important for today's discussion later on. But this is a particular kind of space-based telescope which is rotating around the Earth in stable circular orbit and giving us huge amount of data. But as I said, this is just one representative example. I will talk about other space-based telescopes or artificial satellites in due course. Just to zoom in and just to show you how complicated these telescopes are, this is just 10% of the Hubble Space Telescope. And as you can see, if you look in very carefully, you can see that there is a guy sitting over there and fixing the telescope, fixing a part of the telescope. And this part is just roughly around 10% of the total telescope. So from here, you can imagine about the size and technology and the complications of this telescope, and just try to think over it once again, that this huge amount of telescope with huge amount of technological complications and etc., that has been placed properly at a particular orbit, and that is rotating around the Earth for the last 27 years uninterruptedly, and that is giving us huge amount of data. So just try to think over the power of human intelligence, how they have built all these kinds of things, and not only that, how you have decoded the data. I'll talk about that in due course, how they have been able to decode the data that is available from telescopes, and how they've been able to understand about the outer space, so to say. And one particular example for ground-based telescope is called the South Pole Telescope. That looks like this. Come on, this is not too impressive for sure. Why this is not that impressive? Because as I said, this is underground. This telescope is underground. This is located, as you can see, there is ice all around. This is South Pole. And this telescope, this particular telescope, South Pole Telescope, that has been placed 1 kilometer deep inside the South Pole. And all you can see is just the tip of the telescope. The major part of the telescope is there underground, 1 kilometer down the ground level of South Pole Telescope. If I zoom in, then you can see that some part looks like this. But as I said, this is just the tip of the telescope. Most of the part is there in the underground level. Okay, so this is one particular example of underground telescope. So as I said, I will come across other different kinds of telescopes in due course, but I just wanted to give you some example of these different kinds of telescopes, so that you can appreciate the kind of technological developments that have been done for the last 300-400 years or so, and we are armed with this highly equipped telescopes, and using that we will basically try to understand the outer universe, so to say. Good. As I said, now let me come to the science part. So as I said, I will try to give you a chronological development of our understanding about the universe, mostly about the breakthrough of research for the last 100 years or so, starting from Einstein's theory of general relativity And this is the first breakthrough that we obtained back in 1929. Just to give you a historical perspective, general theory of relativity came into limelight in 1915 and 1916. After that, there are three major successes of general theory of relativity, which I'm not focusing on right now. One is the perihelion precession of Mercury, the other one is bending of light, and third one is the gravitational redshift. I'm not coming into that. In my understanding, that is, our universe is expanding. That is the first major breakthrough of research using telescope, and this basically changed our understanding about the universe thoroughly. Okay, so let me come to that point slowly and slowly. So let me go back to our night sky that we've been able to see using our naked eye. And what we have been able to see is our outer sky that is made up of millions and millions of stars. So now, using these telescopes, we can zoom in and we can see that there can be objects in the universe which are actually collection of millions of stars. Not only that, our own solar system, our own sun, that is also a part of one such collection, and that collection is called a galaxy. So we have our own galaxy, which is called Milky Way. You can see this galaxy even with naked eye if you go to Ladakh. Okay, but I mean, using our telescopes and etc., we can look into this particular galaxy to a great extent. And why this is important, I will discuss in a bit details later on. Okay, so all I want to stress upon right now is that in our universe, the next building block is called a galaxy, and we have our own galaxy which is called Milky Way. The sun is just a part of that galaxy. You can just put a dot somewhere, and that dot is a star. So our sun is just a dot in this huge amount of cosmic entity which is called galaxy. This is made up of millions of such dots. Each such dot is a star. So this is our galaxy Milky Way. Not only that, using those telescopes, we have been able to look further. And we have been able to find out that our own Milky Way is not the only galaxy in the universe. In our universe, we have millions of galaxies, so to say. So now we can see some extended objects. Each extended object is a galaxy, and our universe is actually made up of millions of galaxies. So this is our universe as a whole, which is made up of millions of galaxies. Each galaxy is made up of millions of stars. One such galaxy is our Milky Way, and one such star inside the Milky Way is the sun. So our solar system, that is basically located, or our planet, Mother Earth, that is located at a very small corner of this very, very, very huge universe, so to say. Okay, so this is what we have been able to understand, but the point I'm going to focus on right now is this. So this good old man of observational cosmology, Edwin Hubble, I'm pretty sure all of you have heard about his name. He, in 1926 to 1929, during that time, what he was doing using the kind of telescope he had during that era, using that, what he was trying to do is to look into the nearby galaxy. As I said, we are sitting in a galaxy which is Milky Way, and outside this Milky Way we have several other galaxies. So using the telescope, he was trying to look into nearby galaxies, the galaxies which are pretty close to Milky Way. And what he was trying to do is to find out two important information from each galaxy. One information is the distance of that particular galaxy from our Milky Way, and the other one is the velocity of that particular galaxy from that Milky Way. As it turned out, these galaxies, they were not still, they are not at rest. Each galaxy is moving. This is what he found out. So what he tried to do is to find out the information about the distance of each galaxy. These are the galaxies, so you can find out some distances that are written over there. So he tried to find out the distance of each galaxy and the velocity of that galaxy. And then what he did is that he tried to draw a simple plot. Along x-axis, he plotted the distances of individual galaxies, and along y-axis, he plotted the recession velocity of each galaxy. And as you see, there are some black dots over there. Each black dot is a data point which represents a particular galaxy. So once again, just try to imagine one galaxy. We have been talking about galaxy is a huge kind of thing. And now that galaxy is just a data point here. So each data point is a galaxy. And as we found out, what we do in our laboratory as well, when we perform an experiment and we find out some data, what we do is that we first try to draw a curve. We plot all these data points along x and y axis, and then we try to find out the mean curve. Okay, so that we can understand the nature of the experiment that is going on. Okay, so this is precisely what he tried to do. So using all these data points, he tried to draw a mean curve. And to his utter surprise, what he found out that this mean curve is nothing but a straight line. And this has got a profound significance. Because this basically tells you, further the galaxy is from our Milky Way, greater is its velocity. Because this is x versus y curve, and this is a straight line, so dy dx, that will basically give you the slope of the curve. And as you see, the way y is increasing, the way x is increasing, y is also increasing. So further the galaxy is from our Milky Way, greater is its velocity. So essential conclusion from here is that galaxies are actually moving away from each other. So each galaxy does not depend, as I said, it does not depend on where we are sitting and we are looking into the outer space, because we are sitting at a very small corner of our universe. So if there is an intelligent species sitting anywhere else and he or she is performing the same experiment, he or she will also get the same result, that galaxies are basically moving away from each other. That can only be explained from this kind of plot. So what is the physical significance of this? The physical significance of this is dramatic, and this has basically changed our understanding about the universe drastically. There is a paradigm shift over here. It basically tells you, let me just try to give you a simple example, though this example is not particularly correct, but this will serve as this will help us in drawing analogy of the scenario. That suppose you have a balloon in your hand, and you are basically pumping air into the balloon. So the size of the balloon is increasing. What will happen? The points that are located on the surface of the balloon, if you just try to look into some of the points that are located on the surface of the balloon, as the size of the balloon increases, those points are they will basically move apart. They'll move away from each other. So here what happens is that we can see only those points moving away from each other. For the case of universe, those points are nothing but these galaxies. So since galaxies, those points are moving away from each other, the conclusion from here will be that the universe as a whole on which these galaxies are located, that is basically changing its size, that is basically expanding. And because it is expanding, these galaxies are actually moving away from each other. So at this particular point, Hubble, using his data, that data is pretty old, I will come to more advanced data in a minute, but using his data, his conclusion is that no, our universe is not static. That is not like it was just like that millions of years back, and it will be like that millions of years after today. It's not like that. Our universe is changing its size. Not only that, this is expanding. And because this is expanding, we can see that all these galaxies, they are actually moving away from each other. And as I said, this was basically a paradigm shift about the understanding of our universe. Today, after 1929, almost 100 years have passed by, and we are sophisticated with highly advanced telescopes and etc. etc. So right now, what we do is that we use the Hubble Space Telescope directly, using this data from Hubble Space Telescope. This is the latest data, as I can show you. This is this is not the latest data. This is the data coming in 2001, I think. But this is a much more advanced data compared to what Hubble found out in 1929. But here, I'm not going to explain this thing, but just try to understand that all these green points, etc., they are different data points. And using that data point, what people do right now is, once again, they plot distance versus velocity curve. And from here, they're pretty confident that what Hubble proposed at that point is analyzing those recession velocity of these galaxies, that is 100% correct. Yes, our universe is expanding as a whole. But due to the advent of this technology and etc., we have been able to measure the expansion rate to a great accuracy compared to what Hubble did. So what Hubble said qualitatively, that was very much correct, that our universe is expanding, but quantitatively that was not too correct, because the rate of expansion as calculated from his data was not too accurate. And that is why this advent of technology that helped us in understanding our universe to a much better accuracy level. And right now, using the same technology and same technique, same mathematical technique, but using the highly accurate data that we have in our hand from Hubble Space Telescope, we have been able to conclude that, yes, of course, our universe is expanding, but the expansion rate we have been able to measure to a great accuracy compared to what Hubble did. So this is the first success back in 1929. But what I am trying to point out right now is that the invention of science doesn't stop at some point. It just advances over time. So that is the point, what Hubble found out in 1929, that has advanced to a great extent. And right now we are much more convinced with much more accurate data that, yes, indeed our universe is expanding. But not only that, we have been able to find out the rate of expansion to a great extent. So how do you do today? I'll very briefly discuss about that. So how do you measure, first and foremost? How do you measure about, how do you come to the conclusion? Okay. So as we know, from the outer universe, whatever data is coming to us, that is coming basically in form of some waves. Okay. And that are mostly light waves, but with different wavelengths and frequency that I have talked about. So using our telescopes, the telescope can be located on the ground somewhere on the Mother Earth, or that can be located underground, or that can be placed somewhere in space. But using all these telescopes, we basically catch those waves. And those waves, as it has been found out that the wavelengths of the wave that are not the actual wavelengths with which the waves have been emitted by some particular astrophysical object. The wavelengths are getting changed, but this is no surprise. From our good old school days, we know that whenever an object, basically, whenever there is relative movement between the observer and the source, then the frequency or wavelength of the wave that basically gets changed. We know this from our good old school days, and this is called Doppler effect. If the object comes closer to the observer, if the source comes closer to the observer, then the wave basically squeezes, the wavelength becomes shorter. And if it moves away from the observer, then the wave is stretched, so wavelength is gets larger. And we can just measure this change in wavelength. Right now, this is what we do, that we have some laboratory references for different kinds of waves. Like we know what is the wavelength for red light, what is the wavelength for yellow light, what is the wavelength for blue light. We have got the laboratory references, and we know that comes from, say, helium, either from sodium vapor or from helium vapor, everything. So from here we can find out the laboratory references for different kinds of wavelengths, and we can just measure using our telescope the change in the wavelength of the wave that we are catching using our telescopes, and that is actually coming from the outer space. And as we can find out that further the object is, greater is its change in wavelength. Like you can see from here that if there is a star which is located pretty nearby, its wavelength gets changed to slight amount. If there is a nearby galaxy that Hubble did, if there is a nearby galaxy, its wavelength basically changes, stretches, its wavelength increases to little bit more amount compared to the stars. If there is a distant galaxy, then its wavelength is further stretched. And if the galaxy is far apart, this is a very distant galaxy, its wavelength is further stretched. And all this stretching, the wavelength is basically stretching means it goes from blue to red. Because we know from our once again good old school days, the Vibgyor kind of thing, the wavelength for red is the largest one, wavelength for blue is the smallest one, or violet is the smallest one. So the wavelength gets stretched means basically there is a shifting of the wavelength towards red. This is called redshift. So all we can do is, using our telescope, we can measure the exact amount of redshift of the wave that is coming from a particular object. And by analyzing that redshift, we can extract out information about the source. about that particular astrophysical object. It can be a star, it can be a galaxy, it can be a cluster, it can be the universe as a whole, it can be other astronomical object like supernova, etc., etc. I'll come to that point later on. But just try to think over it a little bit. Just try to stop and think over it. Once again, that we are basically located at a very small region of the universe, and using our technological developments, we are basically looking to the outer space, and we are just catching some waves. Just by analyzing those waves, we are being able to understand the mysteries of our universe to a great extent. This is itself pretty surprising, and if you are not surprised, I will request you to be surprised. Okay, once again. So what we have been able to understand, what we've been able to learn, I've talked about that little bit, but we'll talk about that in a bit detail slowly and slowly. This is the second surprise, so to say. This is the second surprise. As I said, in 1929, Hubble basically first found out that our universe is expanding, and for the last 100 years, this has been proved time and again with much more accuracy. The second surprise came in 1933 with the discovery of something which people call today dark matter. I'll come to that point in a minute, slowly and slowly. Okay. So as I said, I'm not going to details of everything. I'll just tell you the story of development of this subject historically. Okay. So let me come back to our own galaxy, Milky Way. We have already seen that this is our galaxy. This looks like this. This is made up of millions of stars and etc. etc. If you look into our galaxy from a different perspective, it looks like this. So this is just a cross section of the galaxy from a different angle, and that looks like this. This serves as a very important information in the discussion we are doing right now. So this galaxy, as we know, this is our perception that, as we have seen, the sun is spherical, earth is spherical, most of the stars are spherical. So it appears to us as if all these astronomical objects are spherical. No, all of them are not spherical. They can be elliptical kind of shape, they can be arbitrarily shaped, and etc., etc., and they can have a particular kind of shape. They can be of disc-shaped. And our own galaxy, that is a disc-shaped galaxy. This is very important. This is called spiral galaxy, and we have been able to find out millions of spiral galaxies in our universe. So this is just a particular example. So why this is important? Because this spiral galaxy, it has got a center. That center, in the center, this is more or less a spherical bulge. This is a spherical object in the center, where most of the stars and etc. etc. are located. But you can see lots of arms there coming out of the center. And these arms, they basically, that cumulatively basically form it a disk. It's not a spherical one. As a whole, this forms as a disk. And what are these arms made up of? They are made up of neutral hydrogen. So they are clouds of neutral hydrogen. We have been able to find out this thing for millions of galaxies. I am giving you one particular example, that is our own Milky Way, but rest assured that this has been proved beyond doubt that this is true for millions of spiral galaxies, that for all these galaxies, these arms, they are made up of neutral hydrogen. Not only that, we have been able to measure that thing very accurately. I'm coming to that slowly and slowly. Okay. So as we know, neutral hydrogen, this is once again from your good old school days, you know that hydrogen, that is the simplest possible atomic structure we can have. Inside the center, it has got a proton, and outside the proton, electron is rotating around this thing in a particular orbit. Okay, and as you know, they have got fundamental properties. These protons and electrons, they have got fundamental properties like spin. So what can happen? Both proton and electron, they can be spin up or spin down, or one can be spin up and the other one can be spin down. This is something we know from our good old school days. And also we know that these two states, like if both of them are in the same spin or they are in the opposite spin, they have got slight energy difference between them. So we have been able, using our telescopes, we have been able to find out that 80% of visible matter in the outer universe is made up of neutral hydrogen, first and foremost. So all these tails and etc., they are made up of neutral hydrogen, and they constitute to as much as 80% of visible matter. And all of us know this neutral hydrogen has singlet and triplet state that I have already talked about. And because of this slight energy change, there is spontaneous spin flipped between them. And we know about that thing. Those of you who are already in the UG and PG level physics course, we know that this is called hyperfine splitting. So due to this energy change, they transform from one state to other. And as they transform from one state to other, there is typical energy release or energy absorption. And this amount of energy radiated or energy absorbed, that has got a typical frequency of 1420 megahertz. This is something we know for sure. 1420 megahertz. So this is the frequency. If you transform to wavelength, the wavelength becomes c by frequency, right? C is the speed of light in vacuum. And that becomes typically 21 centimeters. So the kind of wave that is coming out of that, either being absorbed or being emitted, that has got a typical wavelength of around 21 centimeters. As I said, just try to compare this thing with your optical kind of wavelength. Okay, the visual that has got a typical wavelength of 10 power minus 4 centimeters. So this wavelength of this kind of observation, that has got a much bigger length compared to the optical. So that is why we cannot see these waves using our optical telescope, and we need to build different kind of telescope that we have already talked about. I will come to that point slowly. We need to build radio telescope in order to observe them. Using the radio telescope, what we can do is that, I'm not coming into details of that, what we can do is that we can just catch those waves once again and we can extract out physics from them. So what we can do is that we can plot along x-axis the rotational velocity, the distance of each. I can consider that there are so many objects, they are rotating in stable circular orbit around the center of the galaxy. So all these objects, they can find out the distance from the center, and along y-axis we can find out the velocity of that object. And we can draw a curve, just like similarly what Hubble did. We can draw a curve over here. So you can measure the rotational velocity and we can draw a curve. Okay, and I'm not going into details of that, but just using, even forget about general theory of relativity, using your Newton's law of gravity, if you can explore that thing, it's a simple pen and paper calculation. You can find out that you expect that the plot of velocity versus distance shall look like the one which is in the bottom, that is written expected from luminous disk. This is what you expect from your understanding of science based on Newtonian gravity or general theory of relativity, so to say. But observationally, what people found out is significantly different one, and that is the plot in the upper one, so to say, which there is written this is the observed one. So these are the data points that we have been able to find out observationally, and this is the plot we expect theoretically. And as physicists, since physics is an experimental subject, we will believe on experiments. We'll perform the experiment several times, and that is what people have done. As I said, there are millions of galaxies. For each spiral galaxy, this experiment has been performed several times, and for almost all of them, barring only two very recent exceptions, for almost all of them, we have been able to find out that there is a huge discrepancy between what you expect from your theoretical understanding and what you get from observation. And that's why this served as a pretty surprise. And once again, this is a breakthrough of research in today's cosmology or understanding of our universe. It basically tells you that the only way by which you explain this discrepancy is by considering that outside the spiral galaxy, there is a huge amount of unseen matter in form of a halo, and that matter is called dark matter. So right now the conclusion is that whatever we can see, that our own galaxy or there are other spiral galaxies as well, they are disk separated. So far as the luminous matter is concerned, whatever we can see using our telescope, that luminous matter is disk separated. But my observation tells us that along with those luminous matter, we have outside the galaxy a huge amount of unknown matter that is called dark matter, and that matter is actually responsible for this extra acceleration that pushes the curve up, that stops the curve to fall down. And that is why this extra amount of acceleration is being given by this matter, which is called dark matter. Okay, so that was once again that served as a new breakthrough. And just try to understand once again that using our telescope, it may so appear, I mean, all of us can have this idea that using our telescope, what we do, we basically project the telescope to the outer space and we just try to find out whatever is there. But right now, see, this is pretty surprising. Why this is surprising and why I call it a breakthrough? Because here we can see is that whatever we can directly see using our telescope, apart from that, there can be huge amount of unseen matter in our universe that can be felt. Since this is matter, this gives you a gravitational force, so to say. So that gravitational force, due to the gravitational effect, that can be felt through the waves that are basically coming from them. And just by analyzing those waves, just by analyzing that data, we can conclude about their amount, about their distribution, about their so many things. Just that we are not being able to see them directly. That is why this is called dark matter. And who discovered that? Vera Rubin. That was not discovered in 1933. I'll come to the 1933 later on. This was discovered much later. But I have taken it as the starting point for dark matter because of this thing. This was discovered by Vera Rubin. And if you recall, at the beginning of my talk, I talked about Vera Rubin Observatory. She was a young graduate student at the time. And using her telescopes, she first found out that, yes, of course, there is a huge discrepancy between our expectation and what we observe. And almost nobody believed her. It was a guy called Zwicky. I'll come to his point in a minute. He was a famous scientist, famous astronomer around that time. Zwicky first took her seriously, and Zwicky explained that, yes, of course, this is true, and this can only be explained by considering that outside the galaxy, there is huge amount of unknown matter in form of dark matter. And this is pretty unfortunate that she left us 2-3 years back without getting a Nobel Prize. So just to honor her discovery at that time, we have given this telescope a new name, which is Vera Rubin Observatory. And this is just particularly for the younger people they are listening to my talk, that look, she was pretty young when she discovered this thing. So at this young age, you are basically expected to develop this kind of surprising things, to come with this kind of breakthrough researches, etc., etc. So don't just shy away because you are young. Okay, don't just shy away with your new ideas and etc., etc. Try to come up with whatever you have understood, and maybe someday that will basically lead to a new breakthrough, so to say. Okay. So let me come to this point now. What Zwicky did in 1993. Okay, I talked about dark matter. Once again, this was the first hint of dark matter. So as I said, along with our galaxy, there are several galaxies in our universe. And now, collecting these galaxies, you can see that there can be a collection of galaxies which is called clusters. So our universe as a whole is constituted of several galaxy clusters. Each galaxy cluster is constituted of several galaxies. Each galaxy is constituted of several stars, and our sun is one just star. Just keep this in mind. So these are just the building blocks of our universe. Gradually bigger and bigger blocks. I talked about sun, I talked about star, then I talked about galaxy, and now I'm talking about galaxy clusters. So Zwicky, what he did in 1933, Zwicky looked into the galaxy clusters, and he tried to measure the velocity dispersion. Don't just get confused with these names. Velocity dispersion essentially means, as I've already talked about, every single object of our universe is moving. Nobody is static. Everybody is moving. So this velocity dispersion means essentially the relative change in velocity, relative separation, or relative what should I say? I mean, the velocity is not uniform for all of them. Okay. So this delta of velocity, relative change of velocity, Zwicky tried to measure that. This is called velocity dispersion. And from here, he basically, this is a simple pen and paper calculation. But as I said, my intention is not to go into the mathematical details. I just try to show you these pictures and etc. From there, I'll try to draw the conclusion. So using simple mathematical calculations, we can find out from this velocity dispersion the total mass of the cluster. Okay, so using the velocity dispersion, Zwicky found out the total mass of a particular cluster, so to say. And then once again, using our telescope, we can see whatever is there. That is called the visible matter. So Zwicky found out what is the total amount of visible matter, total mass of the visible matter. So now, if the cluster is made up of visible matter only, then the measurement of mass from these two different methods, they should match each other. Let me once again repeat. Once the mass is measured from the velocity dispersion, and once the mass is measured by collecting all the visible matter taken together. And if the cluster is made up of only visible matter, then these two masses should be equal to each other, more or less. But what he found out, to his utter surprise, that there is once again a huge amount of discrepancy between these two masses. The actual mass of the cluster, as measured from velocity dispersion, is almost 5 times the mass of the visible matter that you can see directly using our telescope. So right now the conclusion is that maybe around 4 times of visible matter in any galaxy cluster is made up of some unseen kind of matter, which Zwicky for the first time gave the name dark matter in 1933. So the conclusion is that dark matter must be there in individual spiral galaxies, and that must be a huge amount. Dark matter must be there in bigger building block like galaxy clusters. And not only that, dark matter must be the dominant contribution that should contribute to around 4 times the mass of visible matter in spiral galaxy or galaxy clusters. So that's why I say this is once again a breakthrough of research. This basically tells you that using our telescopes, whatever we can see, there can be huge amount of unseen matter in our universe. But since this is matter, we can feel its gravitational effect by measuring the waves that are coming from them. And just by measuring, but just by analyzing those waves using our telescopes, we have been able to conclude about their quality, quantitative, as well as distribution, property, etc., so on and so forth, to a great extent for the last 100 years or so. Once again, I'm not going into details of that. But all I want to stress upon here is that this is the second breakthrough after Hubble's discovery of expanding universe, that in our universe there can be huge amount of unseen matter, which is generically called dark matter. And with the advent of telescopes and etc., we have been able to know about them further and further with much more accuracy, with much more bigger perspective. I'm not talking to that in details right now. I'll come to this point later on. This is another observation for which gives you a direct hint of dark matter. This is called Sloan Digital Sky Survey Telescope. I'll come to this point later on. But this basically tells us that around 25% of our universe is made up of dark matter. So as I said, for each galaxy, this must be around 80%. For each cluster, there can be around 80%. But the universe as a whole, around 25% should be dark matter. I'll come to this point later on. But all I want you to keep in mind is that this is the second surprise, that along with visible matter, our universe does have huge amount of dark matter. Okay. And this is a pretty recent thing, that how to see them. As I said, this is dark. They cannot be seen. So how to see them? This is one proposal, that if two clusters, they merge, they collide with each other. This is called bullet cluster. This was one proposal long back, and this is something that we got by computer simulation, etc., that if two clusters merge, then since dark matter cannot be seen because they do not interact with visible matter to a great extent. So after the collision, we will be able to find out that visible matter, they form a chunk. They collide with each other, they basically interact with each other, and they form a chunk. But since dark matter, they do not collide, they will just move away. So at the end of the day, the end result will be visible matter. If two clusters collide, we can see the visible matter at the center, and we can see all the dark matter outside that. So this was computer simulated, and this is for the first time people have been able, so this is the real data. Okay, that was the simulation. This is the real data. That for the first time we have been able to find out that yes, of course, bullet cluster can be a reality. So this is some data we have been able to find out. I'm not going to details of that data, but this may serve as first proof of dark matter. Somehow, once again, we have this will be an indirect proof through its gravitational interaction, so to say. But all I want to stress upon is that, once again, before going to the next step, that this is the second breakthrough of research of our understanding of about our universe using the telescopes. Okay. So let me stop here for a second and let me try to get some feedback from you guys. Is this all right, whatever I'm discussing, or do you want me to change the pace or be a little bit explicit or maybe a little bit more storytelling mode? If I get some feedback from you guys, that would be good.
Am I audible, sir?
Yes.
So, okay. So,
Is the pace and the way I'm telling
it's absolutely fine, sir. It's absolutely fine.
Okay, thank you.
So we have some questions. Can I ask now or later?
I think I will address the questions at the end of my talk, because
Okay.
I do expect that there will be a lot.
Okay. Thank you, sir. Thank you.
Okay, so the third breakthrough I'll talk about right now. Once again, let me repeat. The first breakthrough was in 1929. The breakthrough was about the expanding universe. Next breakthrough came in 1933 onwards for different observations that basically tells us that our universe is made up of huge amount of dark matter. Third breakthrough came in around 1964-65. This has got a typical name. The name is called cosmic microwave background radiation. Why this is breakthrough, once again I will explain slowly and slowly. But once again, let me assure you that don't bother about these names. Each word has got some significance, some meaning, but don't bother about that. Okay. All I want to stress upon is the invention about our universe using our telescope. And this invention is called cosmic microwave background radiation. This was discovered in 1963-65 by two guys, Penzias and Wilson. I'll come to that. That has got a fascinating story. I'll come to that story in a minute. But before that, let me tell you what kind of telescopes we use for this nowadays. There are lots of telescopes. Penzias and Wilson, they used a telescope in Bell Laboratory in USA. That was a pretty old one. I'll come to that point. But after that, they found out this is basically a gold mine. So in order to know about that gold mine, a bit details, people propose different telescopes. One such telescope is called COBE. After that, two most advanced telescopes came. One is Wilkinson Microwave Anisotropy Probe. All of them are space-based telescopes. So they are artificial satellites. So this is Wilkinson Microwave Anisotropy Probe. This is NASA's initiative. And the second one is called Planck. This is European Space Agency's initiative. Both of them are space-based, and they're highly sophisticated with advanced technology, and they're giving us huge amount of precise data with unprecedented accuracy. I'll come to that point later on, slowly and slowly. This is one proposal, once again, from the Indian community, and I am also part of this proposal, that this might be a new CMB mission in the next decade or so. This is just in the proposal stage. The scientific part is still under discussion, and etc. We have made a proposal to ISRO to build a new space mission, particularly dedicated to CMB observation from the Indian perspective, so to say. This is still in the proposal stage, and we do hope that at some point this will get some limelight. Okay. Another important telescope for CMB mission is this one, which I have already talked about, but let me once again repeat that this is South Pole telescope. So some telescopes are placed on the outer sphere. They are getting us data. They are artificial satellites. They are getting us data about a particular kind of observation, which is called cosmic microwave observation. I'll come to that point. But there is one particular telescope which is located in the underground, which is South Pole telescope. And that is also giving us huge amount of data about cosmic microwave background. That has got other purposes as well. But one purpose is to give us information about cosmic microwave background. I'll come to that point later. Okay. So there are other telescopes as well, but this is what I'm trying to focus on. Okay. So back to 1964-65. These two guys, Penzias and Wilson, and this has got a fascinating story. These two guys, Penzias and Wilson, in Bell Laboratory in USA, they were trying to measure something using a radio telescope. As I said, the waves that will be coming from here, that has got, I mean, I've given this name microwave, and all of us have used microwave oven in our day-to-day life. The kind of wave that are basically being generated in microwave oven, can we see them? No, we cannot see them, because their wavelengths are much bigger than optical range. So the kind of wave we will be talking about right now, they will have wavelength of microwave order, typically of 2 millimeter length. Okay, so that's pretty huge compared to the optical wavelength, 2 millimeter length, and they fall in the category of radio wave. Okay, so using radio telescope, these two guys, Penzias and Wilson, they have been trying to find out something. Their intention is not to find out this particular observation, but what they found out is that they were getting a disturbing buzzing sound continuously in their telescope. They first thought that this buzzing sound is a noise, because as you know, I mean, all of us know about noise. Okay, just like in our radio or television, we need to tune that, because along with signal, lots of noise comes. We need to reduce the noise in order to extract out the correct signal. Okay, from the outer sphere, along with the signal, there can be lots of sources. There can be different sources of noises. So there can be lots of noises coming. And all we need to do is that in the laboratory, collecting the raw data, we need to extract out the noise properly in order to find out the real signal. That is itself a big challenge in cosmology research or astrophysics research. I will come to that point later on. So what these guys thought, that this buzzing sound, that is actually a noise, because their target was to do something else. So they tried to employ all possible noise reduction techniques to reduce the noise and to extract out the signal, within quote unquote, the signal that they thought is the signal. Okay. But after employing all possible scientific and manual techniques of noise reduction, at the end of the day, what they found is that buzzing sound is still there, that annoying sound is still there. They could not produce that. That was pretty surprising, and at that point, they were pretty skeptical. Then they tried to find out if at all this buzzing sound has some scientific significance. So what they did is that they tried to, from that sound, once again, that is kind of wave they're catching, etc., etc. From that wave, they tried to draw once again a plot. Along x-axis, they drew the frequency of the wave, and along y-axis, you can see in the bottom there is frequency. Forget about there are two plots here. Just concentrate on the upper plot. Forget about the lower plot. Okay, so residual is not important. So along y-axis, you can see the frequency. So along x-axis, they drew the frequency, and along y-axis, they drew the intensity of the wave. Just out of curiosity, they did this thing. And to their utter surprise, what they found is that all these points and all these dots are data points. This is the data points. And once again, they tried to draw a mean curve. This is what we do time and again in the laboratory. In all these experiments, this is what we do. We just along x versus y curve, we basically put the data points, and then we try to draw a mean curve. To their utter surprise, what they found that this mean curve turns out to be a black body. This gives you a black body spectrum. This is pretty surprising. Why this is pretty surprising, I will come to that point in a minute. But they wrote a paper in 1965. They were not too confident about what they found out. Okay, that paper has got a pretty funny name. Okay, and they were pretty skeptical that this can still be coming from noise. This may not be a signal. But whatever they got, their conclusion is that if we analyze that data, then we are getting a very, very accurate black body spectrum. So the source from where the data is coming, that must be a black body. And that turned out, after huge amount of re-analysis and further investigation, is that data is coming from the earliest possible information about our universe, which people today give it a name, cosmic microwave background. And all it tells is this information. Why I say this is once again a breakthrough. All it tells is that our universe as a whole acts as a black body. Why this is important? This is black body essentially means, I'll come to that point. I'll come to that point in a minute. But before that, let me tell you today. So because that were pretty interesting, people tried to investigate further on that, and that's why I talked about these new telescopes like COBE, WMAP, Planck, South Pole Telescope, and I'll talk about some future missions as well. Using that, we have been able to understand cosmic microwave background to a great extent. First important information you got from here is that our universe, the age of our universe is roughly 13.8 billion years. So our universe is pretty old, 13.8 billion years. And once again, I'll ask you to stop for a minute and try to get surprised and appreciate about the power of human intelligence. We are sitting today somewhere in the corner of the universe, and we're equipped with our technological developments, the telescopes, etc. And we are looking back in time to the universe, and we have been able to understand that about our universe, that our universe is 13.8 billion years old. That we have been able to understand very accurately. I will talk about some other issues we have been able to understand. But before that, let me tell you this. So what did this new telescope did? So these new telescope, they basically, as I said, I mean, all these new telescopes, whenever I say I have a better camera compared to you guys, it essentially tells you I talk about pixels and etc. I have a better megapixel. So essentially, pixel means sensitivity and resolution. Pixel means resolution. So resolution and sensitivity. Each new telescope, it basically improved on the resolution and telescope and sensitivity. And right now we can see that this cosmic microwave background sky that looks roughly like this. It does not exactly look like this because no one was there to look into the sky that day. Once again, try to get surprised that we are catching some waves. And just by analyzing those waves, we have been able to draw the sky very accurately. This is not an artist's impression. This has been scientifically drawn. Just like we draw different curves and plots, etc., scientifically, we can draw this thing very accurately using the data. I'll talk about the accuracy level in a minute, using the data. And this, we are pretty confident that this is the first sky that is called cosmic microwave background, which was way back 13.8 billion years back, and that looks like this. So now let me come back to the black body spectrum and etc. So right now, what do CMB observation tells us, and why I say this is breakthrough? First and foremost, what Penzias and Wilson did, that has been confirmed with much more accuracy that our universe is a black body. So what is the significance of that? Yes, maybe our universe is a black body. So what does it mean actually? So from that black body spectrum, you know how to find out the temperature of the black body using Boltzmann distribution, etc. You know how to find out the temperature of the black body. That has been found out to great accuracy today. The temperature is 2.725 Kelvin at all directions, because the temperature should be same everywhere. So if the temperature should be same everywhere for black body, because in black body photons are photons are thermally stabilized. So in our universe, photons are thermally stabilized. This is the conclusion, and that typical temperature is 2.725 Kelvin today. The conclusion from here about the universe, that is the breakthrough. The conclusion is that our universe looked same everywhere at the beginning. At the very beginning, there was no such kind of thing. There is no discrepancy, nothing. Doesn't matter along which direction you place your telescope, your universe looks exactly same at the very beginning, 13.8 billion years back. This is once again a pretty surprising thing, because before that, I'm not going to discuss the mathematical aspect of this, but before that, the general perception is that yes, our universe is expanding for sure, but this is not uniform. Different parts are different, etc. There can be several different things which are called, I'll come to the cosmic structures later on, but these for the first time said that our universe looks exactly same at the very beginning, not today. Our universe looked exactly same at the very beginning. This was a very important conclusion, and because of that, these two guys, Penzias and Wilson, they got Nobel Prize in Physics in 1978. But After this, after 1965, etc., we have come a long way using all these telescopes. As I said, we have been able to find out we have been able to draw the real CMB sky, and we have been able to find out that the temperature is not exactly same. There is very tiny fluctuation of temperature, but this is really, really tiny. How much tiny? That is of the order of 10 nanokelvin to 200 microkelvin. You can find out the ratio. I say that more or less the temperature of the black body is 2.75 Kelvin, but we have been able to find out very tiny fluctuation of 10 nanokelvin to 200 microkelvin. So you can simply divide this 200 microkelvin by 2.75 Kelvin, and roughly that turns out to be 1 part in a million, 10 power minus 5. So just once again, try to think over this. We are measuring an experiment sitting on the Mother Earth. We are looking back in time using our telescope. We are just catching some waves which are of microwave range. We are measuring some experiment, some phenomena that is happening 13.8 billion years back. There have been so many things that have happened in between, and at the end of the day, we are being able to measure that up to that accuracy, 1 part in a million. That is much more accurate than our laboratory experiments. And that is why I say this is once again a real breakthrough about our understanding of the universe. That we are not only being able to say that our universe looked same everywhere at the beginning, but we have been able to understand our universe to that level of accuracy. The error is really small. So you could have said that yes, if the error is that small, you could have thrown that out. Who cares about 1 part in a million kind of error? But the point is that if you throw them out, you cannot explain the universe as we see today. You cannot explain origin of us as human being, or origin of the sun, origin of the solar system, origin of galaxies, origin of clusters, everything. That is why this is a breakthrough, that from here you can say that everything in the universe that we see today, they originated from those tiny fluctuations. If those tiny fluctuations were absent, then our universe that were same everywhere, that should have looked same today. Exactly same today if those tiny fluctuations were absent. But today we see lots of stars, galaxies, clusters, even us, we can see us. So if those tiny fluctuations were not there, we had not been there. These galaxies, clusters, stars, nothing would have been there. Nothing. Okay, so that gives you a very important breakthrough about our understanding of our universe, that whatever we see today, that comes from this plot. I'm not going to details of this plot. This is a technical plot just to convince you how much technologically advanced we have been able to be, that using all these tiny fluctuations, all these data points, etc., they are real data points. We have been able to get that from WMAP, Planck, and etc., and from these data points, we have been able to extract out physics, and that physics tells you that this is the earliest possible information about our universe, which is 13.8 billion years back. And that tells you that from there, actually, with exact qualitative and quantitative estimation, you can say that whatever we see today, that has originated from those tiny fluctuations. And that is why it actually changed the course of research in modern cosmology. And that is why I say this is the third breakthrough about our understanding of the universe using telescopes. I'm not going to details of that. Cut to 1998. Okay. So once again, let me repeat. At every step, I'll go back and I'll try to repeat this thing. So I talked about 3 different breakthroughs till now. One is the accelerating universe, 1929. The other one is about dark matter, which is 1933 onwards. Okay, as I said, nothing stops over there. All these experiments are going on till today with much more advanced level of telescopes. The third one is about the information, earliest possible information about our universe, which is cosmic microwave background, which tells you 2 most important things, that our universe was exactly same at the very beginning. Photons were thermally stabilized. And not only that, whatever we see today, their seeds were there via those tiny fluctuations that we can see today, okay, in CMB experiments, both qualitatively and quantitatively. That is the third breakthrough. The fourth breakthrough came in 1998, and this is called the accelerating universe, or the generic name is called dark energy. Great. This is called dark energy. I think I should go a little bit fast to cover all these topics. So let me see. So this in 1998, this is called Supernova Cosmology Project. These three guys, Rees, Perlmutter, and Smith, they worked independently with different projects. I've just talked about one project. This is a telescope. Once again, this is a particular telescope which is a space-based telescope which is rotating around the sun. In 1998, these three guys separately. So what they did is that they tried to observe a particular kind of cosmic entity which is called supernova. Once again, let me not go into details of that, but these supernova, they are basically death form of a star. Stars, we see stars because they are basically, there are internal combustions of the star. They are basically radiating energy because of that. And at some point, when the combustion is almost complete, they cannot just withstand their self-gravitational pull, and they at some point explode. This is called supernova explosion. Let me not go into details of that. So all these guys did is that they tried to look into a particular kind of supernovae which are called supernovae type 1a. Once again, let me not go into details of these types, etc., etc. But just to give you the name, the supernovae type 1a, they tried to observe, and what they found out is that once again they drew a plot. I'm not going into details of the plot, okay? But as you can see, all these blue points, etc., etc., they are the data points. Each one of them represent a supernova type 1a. Okay, so at that time, the number of supernovae was really, really small, but things have developed once again for the last, from 1998 to today, almost 23 years, and we have got huge amount of the recent observations are a little bit different. I'll come to that point later on, but at this point, this plot a very recent one. Okay, so this tells you that some x versus y. Along x-axis, I have plotted a quantity which is called redshift, and along the y-axis, I have plotted something which is called distance modulus. I've talked about the redshift earlier. So this plot looks like this. So this is the real plot that we get from data. These three guys got a little bit got a similar kind of plot with little bit less number of data points, but the nature was almost same. And we try to explain this plot once again from theoretical understanding. As I said, whatever we get from data from telescopes, we try to explain that. They tried to explain that, and that basically give you the surprise. Once again, I'm not going to details of this theoretical understanding, etc., etc. But all I want to stress upon is that you cannot explain this plot if you consider that our universe is made up of matter only. By matter, I mean both visible matter and dark matter. I talked about visible matter, I talked about dark matter. So if you consider that our universe is made up of matter only, then you are nowhere close to this observed plot. You can try with different possibilities. The only way you can match this plot pretty well is by considering that along with visible matter and dark matter, our universe must be made up of a third kind of entity which is called dark energy. And that dark energy, I'll come to that point, I'll explain why this is required. And that dark energy is something, once again, that is a fascinating kind of thing, because that came as a surprise. Why this is surprise? Because of this thing. First and foremost, let me explain the surprise, then I will come to the understanding of dark energy. As I said, in 1929, Hubble said that our universe is expanding, and we are more or less convinced that our universe is expanding. But once again, from a theoretical understanding, using simple mathematics from general theory of relativity, you can generically show that our universe should decelerate because of the gravitational pull. That is a simple kind of thing, which I'm not coming into the mathematics. So using simple mathematics, you can see that because of gravitational attraction, even if our universe is expanding, but that should decelerate. The rate of expansion should slow down. But this is for the first time in 1998. These three guys, Rees, Perlmutter, and Smith, they using different supernovae type 1 observation, they found out that no, this is a completely wrong statement. Our universe was decelerating earlier, but very recently our universe is accelerating. The plot basically gives you that information that if you consider that our universe is decelerating, then the plot will not be a concave one. That the plot will not be a convex one. Okay. So this plot essentially tells you, no, our universe is accelerating at present, and this is pretty surprising because, as I have already told you, generically, by considering that gravitational force is attractive, the generic conclusion is that our universe, even if there is expanding, that should decelerate, if this is made up of matter only. So the essential conclusion from here is that so basically accelerating means the size of the universe that is increasing, but increasing at a greater and greater rate. This is jumping and jumping. The size is increasing with jumping speed. So the only way you can explain that is that along with visible matter and dark matter, there must be a third entity which actually gives you anti-gravity, because you need anti-gravity. As I said, gravity essentially results in deceleration. So you must have something in your universe which can overcome the gravitational pull, that should be much stronger than gravity, which can overcome the gravitational pull and result in accelerating phase of the expansion. And that quantity is generically given the name dark energy. So these guys, and they have been able to estimate the quantitative amount of that. I will come to that point later on. But for the first time, once again, this is a paradigm shift about the understanding of our universe, that this basically tells you, yes, of course, our universe is expanding, but there is not decelerating. Our universe is accelerating at present, and there is huge amount of cosmic entity which is unknown, which is responsible for this kind of acceleration that is giving us anti-gravity, that is called dark energy. And for this discovery, these three guys, they have got Nobel Prize in 2011. As technology advanced and we are equipped with much more advanced data. And right now the latest observation is called Dark Energy Survey. This is a huge amount of telescope, that is ground-based telescope, that has given us first round of data, that is giving us huge amount of data, expected to give us much more huge amount of data today. And equipped with all this data, we can estimate the exact level of acceleration of the universe, the exact amount of dark matter, dark energy about our universe, and so on and so forth. Not only their amount, their properties, their characteristics, what they are made up of, everything we are being able to understand from these different advanced sophisticated telescopes. But as I said, at the end of the day, that our universe is accelerating at present, and along with visible matter and dark matter, we have a third kind of cosmic entity, which is dark entity, which goes beyond doubt, that serves as the next breakthrough of the universe. Let me skip some part because I don't have much time. I should finish in 10-15 minutes or so at the most. So let me skip some part. You could have said that, well, from one observation you are saying that our universe is accelerating. That there might be some fallacy in your experiment. Okay, that's why I'm trying to once again take resort of some of the experiments I've talked about. And from all these experiments, you can conclude that our universe is accelerating at present. Not only that, the amount of dark energy that is required from acceleration, that is more or less same. I'll talk about the amount, that is roughly 70% of the universe. I'll come to that point, but let me just give you these names. The cosmic microwave background observation that I have already talked about. As I said, from this CMB sky, you can draw a plot like this. And from this plot alone, these are real data points. From this plot alone, by analyzing this plot, once again, the mathematical aspects I'm trying to skip. Just by analyzing this plot, you can conclude about the individual cosmic entities of our universe, like how much amount of dark matter is present, how much amount of baryonic matter is present, how much amount of neutrinos is present, how much amount of other things are. Similarly, how much amount of dark energy is present. So using a completely different observation, which is cosmic microwave background observation, from the height of the first peak, you can say that the amount of dark energy that is present today is around 70% of the total cosmic budget. And this is what you get exact, almost same amount from the high redshift supernovae. All I want to stress upon is that they are completely two different observations. They are focusing on two different era of the universe. High redshift of the supernovae is a pretty recent phenomena. They are basically focusing on very recent phenomena, and this is a very old phenomena, 13.8 billion years back. But they are pretty consistent. Both of them are saying that our universe must be made up of 70% of dark energy. The third observation, I talked about Hubble Space Telescope, and also once again from this data, I did not talk about that earlier, but all I want to stress upon is that This data, I have shown you this data from Hubble Space Telescope, and this not only gives you information about the expansion rate of the universe today, but also it gives you the amount of dark matter, amount of total matter and dark energy today. And this also tells us independently that our universe must have 70% of dark energy. And there is another observation which I talked about in a different context, which is called large scale structure, that also tells us that our universe is made up of 70% dark energy. So that's why I say we have 4 different breakthroughs. Once again, let me go back to that. One is 1929, our universe is expanding. Second one is 1933 onwards, that our universe is made up of dark matter, huge amount of dark matter. Third one is 1964-65, when I say we found out that the earliest possible information is cosmic microwave background observation, which tells you that our universe is a black body, and everything we see today originated from tiny temperature fluctuations of that black body. Fourth breakthrough came in 1998, that our universe is accelerating at present, which was quite unusual, and the entity that is responsible for acceleration, that is for dark energy. We have got different evidences from dark energy for dark energy from different telescopes, etc., etc. And this is one such evidence. I talked about dark matter, and at that point I referred to this. This is called large scale structure. This was, from the era of Hubble, this is giving us hint that our universe does have large scale structures in form of galaxies, clusters, etc., etc. But the major survey came in 2000, so to say. That is a very recent one, and that is called Sloan Digital Sky Survey. I talked about this thing, and I said at that point that I will come back to this telescope. Okay, this is called Sloan Digital Sky Survey. I'm not going into details of that, but using this survey, we can see about the large scale structure of the universe, and this is what it tells. Okay, just take home this message. It basically tells you. So this is sort of cartoon once again. It basically, from left to right, you can consider that the arrow of time is from left to right. That means at the rightmost we are sitting today, and leftmost is the origin of the universe. Okay, so universe originated through some phenomenon. I'm not coming into that, but we found out cosmic microwave background observation 13.8 billion years back. After that, there is something called dark ages. I'm not focusing, but after that, we see there are lots of cosmic structures in form of galaxies, stars, planets, clusters, etc., etc. And all these cosmic structures we have been able to find out very, very accurately, starting from the era of Hubble to the era of SDSS, where we have some other observations as well, like 6DF, etc., etc. I'm not coming into details of that, but all these things we have been able to find out very, very accurately, and this gives us the next breakthrough through this thing which is called baryonic acoustic. I'm not coming to this because I don't have that much time, but all I want to stress upon is that from this baryonic acoustic oscillation data, I can draw a plot, which is the bottom one. You have already seen about the plot, which is in the top one. The top one is from CMB observation, and the bottom one is from large scale structure observation. It basically tells you that our universe, that is homogeneous and isotropic, that is everything is same uniform at the largest scale that we get from CMB. But today we have lots of inhomogeneities in our universe. We can see lots of cosmic structures. So we need to measure that. We have been able to measure that how much amount of cosmic structures are there in our universe, and how they are distributed, whether they are evenly distributed or oddly distributed, or what can be the other properties, etc., etc. I'm not going into details of that. That is itself a fascinating story. But all I want to stress upon is that why this is fascinating, why this is breakthrough once again, because from here, just come to the uppermost corner over there, that from SDSS data, that is large scale structure data alone, we have once again been able to convince that our universe has roughly 4 plus 26%, that is 30% matter, and it has got 70% of dark energy. So that is why I say we can see the cosmic structures today, and analyzing that we can conclude about the origin of both dark matter and dark energy. And that is why this is once again another breakthrough. After that, so this is all said and done. I'll come to two more breakthroughs very briefly in a few minutes. But before that, let me just tell you. So these are the cosmic constituents as we have been able to find out. Okay, just let me summarize. This is called cosmic pi, and the non-blue part, that is the visible part. This is the most important thing. Whatever we see today using our telescopes, all these stars, galaxies, neutral hydrogen, whatever we call it, neutrinos, etc., that just form this non-blue part, which is roughly 4 to 5% of our universe. The sky blue part is the dark matter, which is around 25%, and the deep blue part is the dark energy, which is around 70%. So, using all these telescopes from different observation, different telescopes, highly accurate data, everything, we have been able to collect all this data, and from all this conclusion, this is more or less, we are more or less convinced that our universe is made up of roughly 4 to 5% of visible matter, 25 to 26% of dark matter, and 70% of dark energy. Okay, so let me spend very little time on these two, the latest breakthroughs, and then I will finish, so to say. Okay, after that, 2015, the next breakthrough came in 2015 in name of gravitational waves. I will not go into details of that, but I'm pretty sure these are very recent phenomena. So you have learnt about this in internet or newspaper or any other medium. This is pretty this is pretty well-known phenomena today. That LIGO, this is a particular kind of interferometer mission that basically found out the gravitational waves. This is placed, I'm not going into details of that, in 1915. So this is basically LIGO. This is how it is made up of. Just to give you a picture of what is going on, but I'm not going into details of that. There are two arms which are far apart, 4 kilometers. Length of each arm is 4 kilometers, and we are basically throwing some laser light from some point. And in our universe, there are two. Suppose I mean the data is coming from merger of two black holes. So there are two black holes. The data is coming, and because of that, some kind of wave is coming. The conclusion is that that wave is actually disturbing the laser light, and we can measure the disturbance through interferometer measurement. Okay, usually you expect destructive interference, but here we see because of the disturbance in the length of the wave, basically at the end of the day we do not get destructive interference. So from the interference pattern alone, we can conclude about the gravitational wave. Okay, this is very briefly I'm telling. I'm pretty sure that this will be obvious, but because you have heard about or you have read about that thing very well for the last few years, I'm not going into details of that. So all I want to stress upon is that LIGO, for the first time in September 14, 2015, they found out gravitational waves, which was proposed 100 years back by Albert Einstein, but we have not yet been able to detect that. In 2015, for the first time, we have been able to detect gravitational waves from binary black hole mergers. Okay, the last breakthrough I'll talk about in 5 minutes, and I'll finish, is black holes. This is even pretty recent, 2019. Just try to think about this because I will come to these dates in a minute. So black holes in 2019, as you know, I'm quite sure you have heard about black holes. That is also a generic prediction from Einstein's theory of relativity. But we were getting so many theoretical developments of black holes, etc., etc. But we were not being able to directly detect black holes or their signature, so to say. In 2019, for the first time, we have been able to detect something, and I'll spend 4 or 5 minutes on that, and I'll finish. The kind of telescope with which we have been able to detect that, this is called Event Horizon Telescope. This is made up of 11 radio telescopes around the world combined. Just try to think about this. Radio telescope is something I've already discussed. Okay, they will catch waves which are the wavelength of which will be much bigger than the optical range, like the kind of disc antenna we use in our home to see TV and etc. So these are much more advanced level of disc antenna. I'll come to this picture, but just to keep in mind, this is not a single telescope. This is a combination of 11 radio telescopes around the world located at different continents, including the South Pole, North America, South America, then Asia, Africa, Europe, etc., etc. And all of them are each one of them are collecting data separately, and then finally at the end of the day, they have been able to collect all this data and extract out information, because the visibility, the sky coverage will be increasing to a great extent to get us this data. This is just to zoom in all these kind of telescopes. Each one of them is a radio telescope, and this is one particular radio telescope, as I said. So I talked about 11 radio telescopes, and this is one particular radio telescope. As you can see, each particular radio telescope is not a single disc antenna. This itself is a collection of disc antennas. This is called array of disc antenna. They have been placed at a particular distance with particular angle, etc., etc. So each particular radio telescope is a collection of disc antennas, and we are talking about 11 such radio telescopes taken together. And taken together, what they have done is this. I will come to this point very briefly, and let me go back to our own galaxy, Milky Way. As I said, our Milky Way is made up of, if you can recall at that point, I said our Milky Way is made up of millions of stars, but not only that, it is made up of something else as well. I will now talk about that something else. That is the latest discovery, that using this Event Horizon Telescope in April 10, 2019, the teams led by YAAS and Genzel, okay, they found out that in just at the center of our own Milky Way galaxy, there is a supermassive compact object called Sagittarius A star. By all these properties, that is called black hole. They, for the first time using their radio telescope, they found out the exactly outer surface of the black hole. This is called the shadow of black hole or black hole horizon. I'm not going into details of these names. But why I call this a supermassive? Because they've been able to measure the mass as well. The mass is 4 million times heavier than the sun. Just try to imagine one single object which is located at the center of our own galaxy. This is 4 million times heavier than the sun. And this team, Event Horizon Telescope, they, for the first time, they found out exactly the shadow of the black hole. Why they didn't? I mean, this is pretty misleading. That's why I'm stressing on this statement. I mean, maybe in many places you have come across, you may have come across this statement that we have been able to see black hole. No, we have not been able to see black hole because we cannot see black hole. The name is given that way because I'm not going into details of that. That is a completely different story. The name is given that way because black holes do not emit any kind of light. That is why this is called black. So since they do not emit any kind of light, we cannot directly see them. All we can see is exactly the outer surface of the black hole or the horizon of the black hole. And this team, they for the first time found out the horizon of the black hole, which is located at the center of our own galaxy for the first time in April 10, 1929. This is something, let me skip this part because I don't have much time. But not only that, this is not an exception because at the same time, they found out the horizon or the shadow of another black hole which is located far away. That is a completely different galaxy which is called Messier 87 galaxy. And they found out that inside the Messier 87 galaxy, there is a black hole, and they found out the shadow of the black hole as well at the same time using the same Event Horizon Telescope. As our theoretical calculations say that inside each galaxy there should be a black hole, which is called a supermassive black hole or active galactic nuclei. So that was proposed long back. The theoretical developments are there, and in 2019, for the first time, they found out that yes, indeed, this is true, and that is why this served as once again another breakthrough. That in our universe, these funny objects which are called black holes, they do not emit any kind of light. We have heard about them to a great extent, and we have been able to find them out, even though not directly the black holes, but the shadow of the black hole using Event Horizon Telescope very, very recently. And that is why this serves as the last surprise or last breakthrough about our understanding of our universe using the telescope. And this is just a follow-up. In the next year, just last year, and let me tell you that because of this invention, this YAAS and Genzel, they shared the Nobel Prize with Roger Penrose, Nobel Prize in Physics in 2020. The last Nobel Prize, they shared this thing. And this is just a follow-up experiment of that. This has been running for the last 30 years or so. This is European Southern Observatory at Chile. This is an optical telescope and not details of that, but this has got a particular telescope which is called Very Large Telescope. Using that Very Large Telescope, they have got another evidence of black hole. They basically found out that for the same Sagittarius A star black hole which is located inside our galaxy, they basically found out that this found out basically the paths of the stars around this black hole, and this is called dancing of the stars around the black hole. For the last 30 years, they have taken all the images and they have combined the result, and they basically released the data in April 16, 2020, just 1 year back. And they found out exactly what was predicted by Einstein's theory of relativity. And that proves once again that yes, indeed, in our universe, we have got lots of black holes. So we have 3 different evidences of black hole. I'm not going into details of that, and I'll finish in a minute, so to say. So having said and done all these things, all I wanted to stress upon, once again, let me repeat, is not to go into the technical details of any particular observation, but just to give you an overview about our understanding of the universe, in particular the mysteries of the universe that we have been able to understand very, very accurately, both qualitatively and quantitatively using telescopes. Now, as science students, you may have asked that almost everything is known. So is there any surprise left? The answer is most of the surprise is yet left, because our universe never stops in surprising us. So in order to find out those surprises, there are lots of future missions which are planned, and they are going to operational in the next 10 years or so. I'm particularly telling you for those guys who will be interested in working in astrophysics and cosmology as they're in their PhD life and so on and so forth. They will be willing to take up this as career. So this is just some names. You can just go into details of their websites, etc., etc. So all these missions are coming in the next 1 decade or so. Some of them, these are all cosmic microwave background observation, CMBS4, LIGHTBAR, Core Quad, CMB Bharat. I have talked about that. There are Hubble parameter estimation. I talked about Hubble Space Telescope. This is the new one, JWST, which is coming. The third one is about large scale structure observation. There Euclid and Gaia. There is this something called 21 centimeter observation. I talked about that. This is SKA, Square Kilometer Array. And the last one is gravitational waves mission, which are ELISA and Einstein telescope. So all these missions, along with them, there are hundreds of other proposals which are expected to come in the next decade or so. So this is high time for you guys, the younger generation, to jump into this subject and explore the beauties of nature and come with more breakthroughs, so to say. So I'll stop over here. This is the Square Kilometer Array. I'll skip this part, but just to motivate you, if you want to make it your career, what you need to do, you need to be really, really passionate. Okay, I'll skip these parts. You need to be really, really passionate. First and foremost thing is required is passion. And then, rest of the things are pretty simple. You can do that thing. You can study BSc in physics and mathematics with computer science. You can study, after that, you can study MSc in physics or applied mathematics or astrophysics and take specialization in astrophysics and cosmology. After that, you need to do your PhD and postdoctoral research in astrophysics and cosmology. And once you are done, you will be a practicing scientist working in this field. And I'm pretty sure during your PhD days onwards, some of you might be able to come with new breakthroughs of cosmology and astrophysics about our universe as a whole using our telescopes. So I'll end up with this statement. I'll take shelter of Shakespeare, Hamlet, where he has said that there are more things in heaven and earth, Horatio, than are dreamt of in your philosophy. So whatever we could expect, we could think about, our universe never stops in surprising us, and using our telescopes, our job is just to find out those surprises, and that is what we have been doing for several years, and I'm pretty sure we will be doing that in the next several years, so to say. Thank you very much, and sorry for overshooting. Now I'm ready to take up some questions if you have.
Thank you, sir. Thank you so much. And what would be so great than ending it with a Shakespeare quote? So there are so many questions. Before that, let me introduce Orjit. So first question is by Mrinmoy Shah. She asked, what are the advantages of using underground telescope?
Good question. So I'll tell you very briefly. As I said, I will not go into the technical details. I talked about noise reduction, right? So whatever signal we get, all these kinds of waves that are coming from outer space, so to say, that come with lots of, and along with signal that comes with lots of noises. Like there are different kinds of pollutions, etc., etc. So in the laboratory, when we collect the data, that is called raw data, After that, we need to do noise reduction in order to extract out the real scientific signal, so to say, which we call sound. Okay, so now we don't have any control on the outer space. So we don't have any control on the noise that is coming from the outer space. But we have control on ourselves as well. So the noise that comes from the art itself, our aim is to minimize that noise. Okay, so by putting a telescope deep inside the underground, we can reduce the human noise to a great extent, right? Like the kind of mobile phones we use. Okay, so they basically give. I talked about radio waves, etc., etc. These mobile signals, they basically disturb that signal. They are frequencies. So first and foremost, we need to put all these telescopes at a deserted place. All these telescopes I was talking about, everything is placed at a deserted place, either on top of a mountain or in a desert or anywhere else where the human disturbance is minimal. Secondly, the atmospheric disturbance we need to minimize. Okay. In order to do that, we need to put a telescope either on the outer space or on the top of a mountain or inside the south pole, where the error due to human noise that is minimized, so that we can get more.
Sir, Soham are asking that, sir, why the South Pole telescope is placed below the Earth's surface. That's the reason you told. But I want to know that there is any kind of special thing, that special reason behind this. So putting the South Pole telescope and not the other.
Yes, correct. That is also a good question. Once again, so the first question is why we have put it in the underground. That is pretty sure to minimize the noise. Next question is we could have put it anywhere inside the Earth's surface. Why we have chosen particularly South Pole? This is a very interesting question, because if you look into the outer sky, okay, if you are a sky watcher, look into the outer sky, or if you have sky map, you can see that the sky coverage from the South Pole is much more rich. From South Pole, if we place even for the southern hemisphere, okay, if we place a telescope in the southern hemisphere, the further south the telescope is placed, its sky coverage is much more rich. That means we can extract out much more important information from the outer space if it is placed in the south. And South Pole is the southernmost point where we can place the telescope. Okay, so that is one purpose for putting it there.
So the next question is by Trideep Banerjee. He's asking, are the underground telescopes used only for observing the non-visible part of the spectrum?
I did not talk about non-visible part for South Pole telescope. I talked about cosmic microwave background observation for South Pole telescope. But as I said, South Pole telescope has got other aims as well. Okay. One aim, I mean, all these telescopes, some of them are pretty focused. Their target is to find out a particular kind of observation, particular kind of target they have. And some of them are pretty wide. Okay. So depending on how they are built up. What are their instrumental sophistications, etc., etc. What kind of wavelength range they are going to cover, etc., etc. Depending on that, they can have one single target or they can have multiple targets. Okay, so South Pole telescope has got multiple targets. One target is, of course, to look into the cosmic microwave background. There are other targets as well. Okay, just like I talked about this black hole detection of black hole through event horizon telescope, and I talked about 11 radio telescopes which are acting in unison, they are in synergy, and they acting together, they basically found out the event horizon of the black hole. South Pole telescope is one of them. So that is another target of South Pole telescope. There are other targets.
Ritika Ghosh is asking about, sir, do the clusters have more dark matter than galaxies?
Sorry, can you repeat the question?
Mithika Ghosh is asking about that. She's asking that, sir, do the clusters have more dark matter than galaxies?
No, roughly the same. Roughly, so far as the material component is concerned, both for galaxies and clusters, roughly 1/5 is visible matter and 4/5 is dark matter. Both for galaxies and clusters. But if you take universe as a whole, then you have this dark energy component which is dominating.
Sir, Aurobindo Dwari is asking, is the dark matter is the only ad hoc candidate or any alternative theory has been proposed?
Great question once again. Great question. First and foremost, let me tell you, this is not an ad hoc candidate. Okay, this is a scientifically understood candidate, and we have got several gravitational signatures for the existence of dark matter. As I have talked about some of them, but there are other gravitational evidences as well. But scientists are really hard to convince, and they are trying to find them out directly as material candidate, either in the laboratory or in the outer space. Unfortunate thing about them is that because they have given the name dark matter, so they cannot be directly seen. Why they cannot be directly seen? Because they cannot interact with light. Okay, we see something if it interacts with light. Like light interacts with something, gets scattered and comes to us. If it does not, then we cannot see them. Unfortunately, these material candidates, even though they have mass, they do not interact with most of the visible matter or with light. So we cannot directly see them, and that has made our life more challenging. Okay, so people are proposing. So what people right now are trying to do, that is completely a different story. I could have said, I could have given a talk on dark matter alone, and there I could have said all the different approaches of finding it out. That is a fascinating story once again. But just to cut it short, there are different proposals. So what people are doing is that they are proposing different models for dark matter from particle physics background, from gravitational background, etc., etc. And from each model, so what you do, that is the part I skipped actually. So what you do in model building, whenever we get the data, we analyze that data, and out of data, we basically give the numerical values of some parameters. By model building, using our theory, we build the model and we try to match those parameters. Depending on how accurately we can match those parameters, we can say how good my model is. Okay. So using this dark matter observations, we have been able to find out some parameters for dark matter, which is called density of dark matter. The relative density, the density parameter for dark matter, the equation of state for dark matter, and all the other properties up there. And based on different theoretical models, we are proposing different dark matter models once again. And from that, we are trying to find out the numerical values of these parameters, and we are trying to match them. Okay. So there are different dark matter candidates, like it can be cold, it can be warm, it can be hot, there can be massive compact halo objects. Even at some point, black holes are considered as dark matter. And then weakly interactive massive particles, this is the most acceptable dark matter candidate today. So all these things have been developed not in an ad hoc manner, but from our understanding of the subject. And each one of them have been subjected to experimental verification. Okay, they more or less satisfy this thing, but till now we have not yet been able to single out one of them. There are lots of possibilities. Some of them have been ruled out, like black holes have been ruled out, machos have been ruled out, hot dark matter have been ruled out, but there is still lots of different models which are still alive. This is one thing. And the alternative answer to this question is that I think whoever asked this question, he or she was trying to point out the alternative thing. Alternative is that it may so happen that we're trying to explain this thing using theory. So maybe we need to modify our theoretical understanding itself. Like we need to modify the general theory of relativity itself. So if we use a new theory of gravity, we will have different field equations. And using those different field equations, maybe we may be able to explain those observations without the need for dark matter. That is generically called modified theory of gravity. There are lots of different proposals for modified theory of gravity, which tries to explain these dark matter observations from theoretical ground without considering any material candidate. But so far, nobody has got great success in explaining all these observations. Like one has explained this one very well, but has failed to explain that. So till now, all of them are open candidates, but till now, more or less accepted idea is some particle candidate for that. But nothing is well settled. And that is your job as young guys to find out.
So,
any other question?
Yes. Sir, Shubhayu, you're asking? Shubhayu Roy is asking, how can we find the mass of a cluster from the velocity dispersion?
That is something. So all these questions are interesting, but as I said, I'm not going into the mathematical and data analysis aspect because that is not possible during this time as well. Okay, that is a technical talk. So let me tell you very, very briefly. Okay, using the velocity dispersion, like as I said, the velocity dispersion is there, all these different velocity dispersion. From there, we can find out the distribution of galaxies inside the clusters. Okay, and from there we basically make use of two equilibriums. One is thermal equilibrium, the other one is hydrostatic equilibrium. All these mathematical aspects I'm trying to skip. Like thermal equilibrium, we know what are the ingredients, hydrostatic equilibrium, what are the ingredients we know. So using this thermal equilibrium and hydrostatic equilibrium, on the hydrostatic on the distribution of galaxies which we get from dispersion relation, we can extract out the total mass distribution of the galaxy inside the cluster. And that turns out to be 5 times higher than the individual luminous matter inside the cluster taken together. Well, simply put, this is the answer. But I'm trying to skip the technical details.
So,
Sir, I have a question. Can I ask, Thomas?
Sure.
go ahead.
So it's in recent times there is a news that some scientists are considering dark matter as the fifth fundamental force, and we already know that dark matter have two special features rather than gravitational matters or anything. They didn't interact. They doesn't interact with electromagnetic particles and waves. And my question is that what's your perception on that? That dark matter can be a fifth fundamental force, and if it is, then there's any kind of predictions already made, or you have any idea about that?
Excellent question. Once again, let me tell you very frankly, I'm a very open guy so far as scientific research is concerned. I don't assume something to be correct or wrong. Okay, I appreciate any idea if this is scientifically channeled towards proper direction, but I do not accept that at the face value. Okay, all I want is experimental verification of that. Okay, so when we say it's a very, very interesting proposal that when we say dark matter do not interact with matter, okay, we basically try to find their interaction with visible matter through 4 fundamental interactions: electromagnetic, gravitational, strong. This is something we know. We have 4 fundamental interactions, and we build our experiments in such a way so as to find out the interaction through either of these four experiments. Okay, gravitational, electromagnetic, strong. But it may so happen that dark matter is actually interacting with visible matter, but through a different kind of force, not through these 4 fundamental forces. Okay, and that basically brought into limelight the idea of fifth force, and that there can be, along with these 4 forces, there can be another force. And if that is there, then dark matter, and if we can find out that interaction, okay, and using that you can find out that dark matter is interacting with visible matter, then maybe that will solve that. So this is just a proposal at this stage. So my take, as you asked about my take is neither a strong yes for this nor a strong no for this. I will wait for experimental verification. This is clear.
Okay.
But till now, just to answer to your question, we haven't found any direct evidence. That is pretty clear. If we find out direct evidence from that day alone, I will say that yes. Okay, but till now we have not yet.
So we have many more questions. Can I take one more, two or two?
No problem from my side.
Okay.
Totally up to you.
Sir, Devdita Ghosh is asking, how is dark matter different from dark energy?
Okay, good question. I've already explained that, but let me repeat because at least for the first lecture, this in many cases this becomes confusing. As I said, first difference is one is called matter, the other one is called energy. By matter, essentially means it has got material properties. Okay, so this is identical to visible matter so far as all the material properties are concerned. Only difference is that it does not interact with visible matter or light. Okay. Whereas dark energy, by simple name, this is called energy. So this is not a material candidate. It has got, I mean, you can attribute a density and pressure onto it for sure, but that density and pressure is not the usual one, not the not identical to different material candidates, as we say, be it cold matter or relativistic matter, whatever you call it. Its density and pressure should be completely different. So far as their properties are concerned, one structures we see today, I said that they are originated from tiny temperature fluctuations in CMB. But if you consider only visible matter, then you need to estimate everything both qualitatively and quantitatively. So starting from CMB, if you come to today, only with visible matter, you cannot explain the exact amount of cosmic structures we see today in form of galaxies, clusters, etc., etc. So in order to explain that, we need to have almost 4 times or 5 times mass of on top of visible matter. That is called dark matter. So this is the role for dark matter. The role of dark energy is completely different. Dark energy does not take part in these phenomena. Dark energy basically helps you in overcoming the gravitational pull and helping the universe accelerate today. As I said, once again, let me repeat, from Hubble's era, so on and so forth, we found that our universe should expand for sure. Our universe is expanding. But generically, from theory, our expectation is that since gravitation is attractive, the expectation is that its rate of acceleration should decrease, rate of expansion should decrease. So it should decelerate. But from observational point of view, we see that this is accelerating. And dark energy helps in overcoming the gravitational pull. So this must be much stronger than the gravitational pull and help the universe to accelerate that we get from observation. So their role is completely different. And so far as the material properties are concerned, they are completely different. Just because they are given, both of them are given the name dark at the very beginning, does not mean that they are equal. Dark essentially means our lack of understanding about those materials. We have not been directly able to find them. That is what it is. Okay.
So next question is the region of baryon number violation can be studied with CMWB?
Sorry?
So is the region of baryon number violation can be studied with CMWB?
Okay, CMB. That is what you are saying. Okay. Once again, this is a very interesting question, and I did not talk about two interesting aspects. One is the thermal history of the universe, because as we have already seen, I have already covered lots of things. So I just tried to skip many other aspects. One is the thermal history of the universe, which is itself fascinating. And starting from the Big Bang, how did the universe? I mean, the universe expanded, and its temperature dies down, and all the material candidates, they were formed at some point. Like at very early stage, they were this ionized state. Everything was ionized, and then from there, basically, atoms were formed. Hydrogens and electrons came together. Protons and electrons came together. They formed hydrogen, and then after that, helium, lithium, etc., everything were formed. And photons, they basically came out of that photon baryon soup, that ion, and they started traveling to us. Those photons are the things which we are catching in cosmic microwave background. Okay. So I did not explain this thing in details. It's a fascinating story. And also I did not explain nucleosynthesis data. This is based on Big Bang scenario. Using nucleosynthesis data, which is called BBN data, we can estimate about baryonic matter, neutrinos, the baryon, antibaryon asymmetry, etc., etc., to a great extent. Okay. So nucleosynthesis data independently tells us that there is huge baryon, antibaryon asymmetry in our universe. And we can, not only that, it basically gives us some hint about the number of neutrino species, etc., etc. All these things that we get from nucleosynthesis data. Now, these baryon, antibaryon asymmetry, we cannot explain in our standard model of particle physics. Okay. So in order to explain that, we need to go beyond standard model. So there are lots of BSM theories using that, like all this dark matter, etc. For all these things, we need to go beyond standard model. Like all these standard model particles cannot explain all these things. Okay, so all I want to stress upon is that not directly from CMB, but an observation which is pretty close to CMB, because nucleosynthesis data is also pretty old data that is coming from Big Bang. Okay, so using nucleosynthesis data, we can talk about this baryon-antibaryon asymmetry, and in order to explain that, once again, we need to go beyond standard. Okay, so just like we need to explain dark matter, we need to explain dark energy, we need to explain this baryon-antibaryon asymmetry. Not only that, we need to explain the presence of sterile neutrinos. So, in order to explain all these things, we need to go beyond standard model of particle physics. Does that answer to the question, more or less? Or?
I hope so, sir. So, Aurobindo Dewari, if you are listening, then comment. So I'm taking one more question, sir.
Yeah.
1 second. So Shogata Das is asking, what role does open star clusters play in a galaxy?
Can you please repeat?
Sir, what role does open star clusters play in a galaxy?
I don't get the question. Open star clusters.
Yeah, yes, sir. Yes, sir.
I am not pretty sure what he means by this phrase. So, it is there.
Okay.
You can
Sir,
explain.
there is another question, so that we can shift to that.
And whatever you think is better.
Okay.
You are the leader here.
Go ahead. Arjun, go ahead.
Deepayan Kole is asking that is there any link between black hole and dark matter?
I've already explained that.
Yeah. Sir.
Okay. So, as I said, dark matter, we have already talked about different gravitational evidences of dark matter, but you need to find out the candidate for dark matter. Okay. So, there are lots of different proposals for dark matter candidate. One such proposal at earlier stage was black holes. But as it turned out, I mean, I cannot just propose. As I said, this is an experimental subject. So I need to estimate everything qualitatively and quantitatively and feed the data very well. Okay, along with the error bars. That is a pretty hard task to do, pretty challenging task to do. Okay, so as we found out that if we consider the black holes to be the candidate for dark matter, it cannot explain all the properties of dark matter as estimated from observations. Okay, so that is why today's perspective is that this is very unlikely that dark matter will act as black holes will act as dark matter candidate. They can contribute partially to dark matter, but they cannot be the sole candidate for dark matter. This is more or less the thing.
So there are so many questions. I'm confused if I'm taking or not. So last question, and we'll end this. So why are the galaxies disc or spiral shaped? Why are all the planets residing in the same plane? Why doesn't it look spherical or ellipsoidal?
Pretty interesting question once again, and I think whoever has asked the question, he or she, if he thinks about basics of physics, he or she will get the answer to that question. First of all, why the art?
I think it's about the centrifugal or centrifugal force.
That gives you the partial answer. The main answer is that whatever shape we get, that we get because everything wants to come to the ground state, minimum energy state. So it depends on the distribution. Most of them are spherical because, as we know, the spherical shape is the minimum potential energy state. Okay, so most of them individual objects are spherical because that is the minimum potential energy state. As it happens for galaxy, internal dynamics is so complicated, so many things are happening. So the minimum potential energy state is the disk shape where all of them are placed on the same plane, roughly speaking. So basic answer to this question is the ground state. Every time, whatever you call it, whenever you talk about the stable state, so to say, if this is not unstable, if this is unstable, okay, this is changing state, that is a completely different ballgame. That has not come to its ground state. But whenever you talk about the stable state, that is its ground state. And ground state essentially does not mean spherical. That is the point we make mistake. Most of the cases we think spherical state means ground state. It depends on the dynamics. It depends on the constituents. A galaxy is made up of so many other things and their internal dynamics is going on, and that is the ground state. There are some galaxies for which the ground state is spherical. That is called spiral galaxies. The spiral galaxies I talked about. There is a reset. There are spherical galaxies. There are elliptical galaxies, etc. Everything depends on what kind of material candidate that particular galaxy is made up of. And if this is in equilibrium, then that is its ground state. Okay, that is the answer to this.
I think we should end here.
Yeah, we should. Okay, sir. Thank you, sir. Thank you so much for joining.
Okay, thank you very much for your attention. And once again, let me thank you for inviting me to this beautiful program. Hats off to you guys for
Thank you, sir.
everything. So I'll be happy to be in touch.
Thank you. Thank you so much, sir. Thank you. Have a good night, sir.
Thank you.
Okay.
So this is
thanks to you all people. Yeah, Roji, go ahead. Thanks to you people also who are joining with us, who are here with us. And that's it for today. Tomorrow we'll be having with us Dr. Bishwajit Chakraborty. He's a senior professor at SN Bose National Center of Basic Science, Kolkata. And the topic will be research in certain fundamental areas of theoretical physics and mathematics. So be there with us. And of course, remember the cause, why we are here today and why we are doing this seminar. It's a part of our solidarity. And if possible, please donate. The contribution link is below. So, Arjit, please.
So there's one thing that Professor Bishwajit Chakraborty just contacted us sometimes earlier, and he is saying that in 2025 there is a celebration in worldwide in science community about the 100 years of quantum physics. So he is already asking us about to promote and recommend Physics Forum Kolkata on there. So this is a very great opportunity for us, and we will also add that topic, 100 years of quantum physics and theoretical physics development, also in this seminar tomorrow. So that's already a good news, and I think everyone is excited for that, for the tomorrow schedule.
Of course.
Be with us tomorrow, and thank you very much for your presence and obviously support for the cause. We know that Bengal is suffering huge problems and huge disasters from the lockdowns, from the Amphan, from the YAAS, and from the COVID 2.0 also, and there is also a possibility of third wave. So we should stand together, stand by all, rebuild Bengal not for a few, but for all. Thank you very much.
Thank you so much. Thank you.